So now we want to represent the solution of forced harmonic vibration in a graphical way. So, or using phasors, we'll do it using phasors. So we start with the equation itself. So in place of sine omega t, we put e to the power I omega t, with the understanding that we'll take the imaginary part of the solution. So now let us take x equal to x bar e to the power I omega t, or x equal e to the power I omega t minus phi, where this x is nothing but x bar e to the power minus I phi. Where x bar is x is real e to the power minus I phi. So x bar is complex, as you know, because the solution cannot have the same phase as the excitation. So there should be a phase difference, and that means x bar has to be complex. So x bar is a real number x into e to the power minus I phi, and when you put that here, this x e to the power minus I omega t minus phi, that means we assume that the displacement that lags the force by an angle phi. Now if you put it here, so you get minus omega square x plus I c omega x plus kx into e to the power I omega t minus phi is equal to f naught e to the power I omega t. So now if you draw a phasor diagram in the organ plane, so first term is this one, kx e to the power I omega t minus phi. So suppose this is your x. So kx and x will be in the same direction. X, so this amplitude is kx, so that means the length of this line is kx, and this angle is omega t minus phi. So this is k x. Now I c omega x. So I c omega x means I means cos pi by 2 plus I sin pi by 2 c omega x, or c omega x e to the power I pi by 2. So that means you have to add another pi by 2 with this, so omega t minus phi. So actually the second term would be along this, which is leading this by pi by 2. So we put it here. And this angle is actually pi by 2. So, and this is actually same as this, but with a negative sign, so it would be in this direction. And so this is 1 and this is 1, and these three should add up to give you this f vectorially add up to give you f naught e to the power I omega t. That means here to here. So this is this is c omega x amplitude wise, this is m omega square x amplitude wise, and this is f naught, and this angle is omega t. That means this angle is phi. Now if you just draw this triangle and apply Pythagoras theorem, then kx minus m omega square x whole square plus c omega x whole square equal to f naught, or x equal to f naught by k minus m omega square whole square plus c, so this should be a root over here. So this is c omega x square root over, so this is the amplitude, and this we have already got. So from this graphical representation also you can verify this, and tan phi is equal to this perpendicular by base. So this is c omega x by kx minus m omega square x, or c omega by k minus m omega. So this is this, and see from here, when omega is very small, this is very small because this depends on omega square x. This is also small, and phi is small. So what we can do is we can take this figure in the next page. Oh my god, we can take this figure in the next page. Yes. Yeah, so this is the general figure, and when omega by omega n is much smaller than this, then kx is large, but this is, and this is further smaller. So this is something like this. So this is kx, this is c omega x, and this is omega square x, and this is phi. So phi is also small. So this is for omega by omega n, it's much smaller than 1, and for omega by omega n, much larger than 1, then this is, so this is say, so the inertia force. So see, this is actually, this m omega square is actually the inertia force, and kx is actually the elastic force, and this is the c omega x is the damping force. So when this omega is large, the inertia force is larger and phi is greater than 90 degree. So and it tends towards 180 degree, but the most important is omega by omega n equal to 1. If that is the case, then the diagram is like this. So this is kx, because this angle is this kx and m omega square x are equal and the phase angle is 90 degree. So whole of the elastic force is balanced by the inertia force, and F naught is F naught. This is F naught. Here F naught is equal to c omega x. So damping controls, the damping balances the externally applied force. So if damping is small, then displacement is small. Is damping yes, so since damping here, only damping here balances the external force, the displacement is high because damping is small generally. So and x equal to F naught by c omega. Okay, so and okay, and also from here we have seen that at damping at resonance, this is x by x static is twice theta. So from here also you can get that. Yes, so if you just continue with this, x equal to F naught by c omega, or x by x static is equal to F naught by c omega divided by F naught by k. So this is k by, or rather one by c omega by k, and that is 1 by c is psi into cc, and for cc we can put twice omega n. So this for c, the psi twice m omega n, twice m omega n being cc, then omega by k. So this k and m, k by omega n square, so this is 1 by psi, this is omega n square. So omega n square, 1 omega n from square goes, so this is 1 by omega by omega n to 2, and since omega by omega n is 1, it is 1 by theta. Omega by omega n is equal to 1, so it is theta. So x by x static is 1 by 2 psi. So this is important and this is also important. So from here you get this. Actually directly you can put omega n here, because this is you can directly put omega equal to omega n here, because omega by omega n equal to 1 is the case, and if you put omega n here, you directly get this. So you can start with, in fact, omega n. So omega n, so this is omega n, then k by omega n is directly cancelled, so you can forget about this. Instead of putting omega by omega n at the last stage, you can get rid of it from the beginning. So this is just C omega n by k. So let us stop here, and we'll again continue in the next class. So this is the graphical representation. I think you now understand the graphical representation. So okay, here at omega by omega n much smaller than 1, the elastic force dominates, and omega by omega n much larger than 1, the inertia force dominates, and here at omega by omega n equal to 1, the elastic force and the inertia force, they balance each other, and the damping force actually take care of the excitation force. So actually you can put the arrow signs here, okay, so which you have missed out. Okay, so thank you.